Thank you. Thanks to organizers for inviting me. Yeah, so I'm going to talk about this done work with Marianne Lawson and Julia Sauter. It's over here in the archive if you want to look it up or check whatever I'm saying something wrong. So I know exact categories came kind of already up in the last two talks, but I still forgive, like, I feel like they only came up like tangentially, so I'll give you a little bit more of an intuition for those who might not be familiar with them. So what is an exact category? An exact category is it refers to an additive category. So this it was added like underlying additive category. When it's equipped with an exact structure, specifically it has a class of distinguished distinguished kernel pairs. This means, so we say L and N. This means L to M is the kernel of Mn, and I and B. I is the kernel of B, E is the co-kernel of I, kernel pairs, and we just pick a class of them. Don't need to be all of them, can just be some of them, and then they have to satisfy some axioms to make them compatible. Those I'm not going to tell you in detail, let's not worry about them too much. And these distinguished co-kernel pairs, I call them conflations. Oftentimes, you also just call short exact sequences or exact sequences. I want to use the word exact maybe for something different. Yeah, in the math so this is an inflation, like this is then called an inflation, and the other one deflation. Others also call them admissible monomorphisms and admissible ecomorphisms. Okay, why should we care about them? So what are good examples? So one reason why they're interesting, so first there's generalization in some sense of generalization of abelian categories, but every abelian category is an exact category. If you take all canonical pairs. However, so by the way, exact categories is exact categories are explicitly an additive category equipped with an exact structure. So they're kind of the same category, just equipped with different structures. So the other one, which showed up in Francesca's talk a little bit, was the split exact structure. So every additive category is also an exact category if you only take the split exact sequences. So this means the ones that are isomorphic to. But then there are many more. So whenever you have an abelian category and you take an extension to a subcategory, that's going to be exact. Yeah, I'm saying abelian, but actually could also just take an extension to a subcategory of an exact category. It's again exact. And the exact sequences are inherited, conflations are inherited by the bigger one. So for example, here, you take, I don't know, projectives or some. Take the subcategory of projectives, that's going to be exact, and it actually is always a split exact structure. But we know obviously the projectives are not in general because maps don't have kernels or co-kernels. However, if you're equipped with split exact structure, you're fine. But then also all modules of finite projective dimension. That's again an extension of subcategory of the category of all modules, and that also is equivalent exactly with a more interesting exact structure. And then one category that came up in Eleanor's talk is the category of MCM modules. She always said it's Frobenius, which actually means Frobenius exact. So it's an exact category with an additional property which makes it Frobenius. Yeah, so these are like the things you could keep in mind going forward when I mention the word exact category. So why am I interested in exact categories? The reason is that it's kind of already enough to do homological algebra in some sense. So a lot of things we do with abelian categories, complexes, derived categories, homotopy categories can do with an exact category already. Maybe I should say at this point, most things you can do, the main thing you cannot do is compute homology. The reason is that you get that in an exact category, kernels and co-kernels need not exist. So, and homology is, yeah, the kernel of whatever it is. It's a kernel or a co-kernel, however you want to view it. So homology might not exist, but we can still talk about when the complexes are cyclic. So when does it have no homology? So a complex is E acyclic. It's let me draw a complex I'm using, and I usually hate it. I'm still going to do it because it's probably the paper in homologic notation. Make sure everyone has their own favorite convention. And so this is a cyclic that we say in degree D, degree N. If the two I mentioned, kernels and co-kernels need not exist. However, so E-cyclic means that the two differentials that start or end in Xn, they factor in a way that first the deflation and then the inflation. So these are the deflation, inflation, deflation. So they have to factor in that way, and additionally, in the terms in the middle, getting to Xn, this that's basically a convolution. So this is a cool, it's one of these distinguished kernel co-kernel pairs. So if this happens, you say something is cyclic in degree N, and we say it's either cyclic, it's either cyclic at grad. And this definition recovers the definition from abelian categories. So cyclic in degree N in an abelian category would just mean, I mean, the inflation is actually the kernel of the N. This would be a co-kernel of this, so all is the same is that the kernel, so the kernel of this, which would be the image, so the image is equal to the kernel. So it's just saying you have zero homology in degree N. Okay, so now using this, we can define the derived category. So if you take the category of complexes, I put the star because at some point I will place it by bounded above, bounded above. But at this point, it doesn't really matter which one. If you assume a bounded, that's conditional which one you assume. So the first thing you can always do, you can always go to the homotopy category. For this, you actually just need that the category is additive. So this is all the morphisms up to homotopy. And then the derived category is the Nadir quotient with respect to all acyclic complexes. There's one tiny problem. So while the so take the subcategory of all acyclic complexes, it is extended, it is closed, it is triangulated, but it doesn't need to be closed under direct summons. So unless you assume some type of frequently idempotent completeness or idempotent completeness, depending on the bounded of conditions. So to kind of resolve this, I don't want to worry about it, I guess that's what I'm saying. I'm just taking a subcategory for all the acyclic and then we close it under direct summons to be sure everything's fine. Okay, so then what things can we do or can we maybe not do that we could do for abelian categories? One thing is T structures. So whenever we have a abelian category and we write down the graph category, we have a standard T structure. Here, this doesn't work. Because so what's the reason for this? We have each T structure that we might want to write down, which has to say, okay, we take our all complexes which are either cyclic in positive degrees. And the negative degrees. And I mean, the first couple of actions of the tree structure are fine. They're definitely orthogonal, and they're definitely closed under extensions. The I is closed under suspension, the core is closed under suspension, everything is fine. The last axiom that we can write everything as if for every object we get an exact triangle from suspension to B, that is not satisfied. So in general, this is strictly this, so this is smaller. The reason is, so how do we usually take or maybe define these truncation functors? We define them by taking a kernel or co-kernel of a differential. However, kernels and co-kernels need not exist in an exact category, so we can't do that. Are there any questions while I'm writing more?
Wait, just one quick question.
Yeah.
This tower operation.
This one?
Yeah.
Sure. This is just basically taking all the extensions. So these are all the X, let me put on the here. Y, such that there's an exact triangle X, Y, Z with X, suspension U, and Z. B. Okay, so now there are some questions we can ask. Can we somehow enlarge this T structure or this thing that's not a T structure to make it a T structure? Let's say when, or maybe how. So maybe the first answer, this was given by Neiman. In general, you can't. In general, the derived value of an exact value does not have to have any T structure. Wow. Maybe let me say non-trivial structure. Because I mean, you could of course take zero and everything is zero. So let's not do that. Also, if you maybe don't have a T-structure, can at least get something that's maximally orthogonal. So let's continue the question. Because we know, so I mean, part of a T-structure is always this condition. This is the orthogonality in the condition, and this holds for the U and V I wrote down. However, the orthogonal, or like the right orthogonal, the extension of the I is in general bigger. So maybe if we can somehow enlarge V to make this the whole orthogonal, and then the other way as well, this would give us what I put it in quotes, maximum orthogonal pair. So this is kind of, yeah. So. And maybe one thing to note for this, because this is somehow, we came from it from this a little bit from a different direction, so we didn't quite start with T-structures, but it ended up having this nice connection. So, but if we have some extent, so if this extends this pair UV, and this is actually a T-structure, or maybe it doesn't even have to be a T-structure, maybe it's just orthogonal. Okay. Then if you look at the heart has to get bigger. And this is actually, and then this will induce equivalent diagram categories. Maybe then you write need to be safe. So we get an equivalent derived category. So this is somehow what we started with. And the input for this is this uses that this inclusion is actually resolving. So the intersection of U and V, which is basically E, that's actually an additive closure of E. This is so this is a resolving subcategory in this U-turtle, it's exactly E-turtle. And that's what, and that's why I already raised the title, but that's why the goal is to find a resolving completion. So something we want to extend E in a way that E is still resolving this bigger thing. We kind of want to extend it maximally, so you can't get any bigger. Everything else embeds into it. Okay, so let me tell you what resolving is and then how we start constructing this category. Okay. So I'll place the name for now. So let F be an exact category. And P an extension closed subcategory. And I take the exact structure. Let's do orthogonal. Okay. And the exact structure on E is the one inherited from that, because it's extension closed. Oh, okay, thank you. And now we say E is resolving in F. If two condition holds, so one for every object in F, we have a deflation onto from something in E. And the second one, that E is closed under kernels of deflation in F. So the thing to keep in mind here, so this is somehow mimicking how we build projective resolutions. And what it's doing is for every, I think, because if we start with some M in F, the first one gives us that we can find the deflation. This is one of our special important functions from an object in E. But now this is the deflation again in F, so it can be kernel. The kernel again lies in F, so we again can project. And I should stick to, so we get a differential. We get a map where M is the co-kernel. This is again E. Then play the game again. Then find an F deflation with X minus E and so on. So what we get is we get a resolution of M by objects in E. And this whole sequence is F specific.
But for this, only use the first property. Is it?
I only use the first property. The second comes up at a different point. Yeah, that's true. Yeah, and then we say E is finally resolving if every M has such a resolution that stops eventually. So why are these things nice? As I mentioned, I'm kind of mimicking the whole taking a projective resolution thing. I mean, that's often very useful, right? It's often enough because of that to look at projective modules. And here what we're basically doing, we're saying it's enough to look at exact modules, but it's enough to look at objects in E. Here they kind of already tell us everything. However, there is a slight issue because we work with exact, because of the exact structure. So like you have to be careful what exact structure we're working with. Because this resolution that I wrote down, I mentioned that it's E is the click. So now if we cut this off and only look at the complex itself, maybe extend it by 0 to the right if you want. This is in general not E cyclic. It's only F cyclic. So if we look at a complex like this and don't know about F yet, we don't know how to recognize them. And this is in such a sequence that we actually can recognize it. It's just like not the cyclic specificity that I just erased, but we need a new notion of what a cyclic means. So this was inspired by the work of Ram, who did like X kernels. So we call it this left X is cyclic. So a sequence is left X is cyclic. If for every map from B to Xn such that this composes 0, there exists a deflation, so this is an E deflation, and there exists a map from A to Xn minus 1 such that this commutes. Yeah. So this is what we call left X cyclic. And this behaves really nicely, especially in connection with resolving subcategories. So if E is the resolving subcategory of F, then I write two things down maybe. So first, every F acyclic sequence is actually, it's definitely left X F acyclic. And this is an equivalent to XE acyclic if all the objects are actually E. I mean, this is the So in other words, this resolution we care about, we know what these resolutions are, even without knowing what F are. We just take all the complexes that are again 0 in positive degrees and then left XE acyclic in negative degrees. Yeah, so maybe some remarks also to kind of tie it back to the V and some. In the revealing chemistry, all of these things coincide. So in some sense, in the revealing chemistry, it didn't do anything new, but in an exact calculation, it actually does make a difference. And then if we look at then left X cyclicity behaves very well. So we can do like if you look at cones, homotopies, homotopy retracts, they all preserve it in the way we would want it to. And I said you could kind of think about this as projective resolution. And one thing about projective resolution is that you can induce maps. So if you try to take two of these complexes, you already have maps in map in degree 0 and degree 1 or degree -1, then you can extend it. However, in this situation, only of course there's morphism. It's maybe just as a side remark because I'm realizing I might be, yeah. Okay. Okay, so now now we can use this notion of affiliation to define a new candidate for a T structure. Construction may be a little bit too big, but we take the U from before and we replace the V. So U is or X is such that and VL is now everything that left X is acyclic in negative degrees. Questions? So so since I've been called, so this whole notion of left cyclicity is clearly not now true. So there is the notion also of right cyclicity. I'm not going to tell you, but I mean that should be easy enough to figure out. However, I intentionally didn't write you where I would take the right cyclicity to define U because that would be orthogonal to the VL. So we really have to do and only do like one side where we change. Okay, and now this pair has a better chance of being a T structure than the previous one I wrote down. So it does satisfy the properties we would want. So most of these are closed under summons, extensions, and isomorphisms. Then U is closed under suspension. L is closed under D suspension. And they are homoorthogonal. And if we can say even more, L is actually the right orthogonal of the suspension of the I in these Japanese. However, in general, this T structure. However, this T structure if E has if in E everything has a X part. So this just makes sure that you can actually take a resolution like this. So for every So this means for every map from N to N, there exists a map from L to N such that L and N is left axis. What this also gives us is resolving completion. So it gives us we now take the intersection of these two. So we call it the left half. And this has actually been defined previously just in special settings. So for example, in a setting where E has all kernels. So these T structures have been found in special settings, but not just and then also LHD is just the restriction of the direct category. And these are precisely these what we call resolving completions, because whenever we have a resolving, so we have again resolving or fully faithful resolving embedding from E into F, and we know, of course, it's always also a subcategory of this LH, which is resolving, which I guess I didn't write down separately. But this is resolving. Then there exists a fully faithful embedding, fully exact embedding, yeah, fully exact embedding. So in fact, we can identify F as an exact subcategory of the half. So in other words, LH of E is universal with this property, with it being resolving. And we can do the same thing for finally resolving. So if you replace resolving by finitely resolving, then this is finitely resolving. And here we have the B, and everything else still holds. Yeah, so maybe let me mention one ingredient, because this is somehow something we'll always want from a completion. So LH of E if you do this construction twice, we didn't do anything. So this is equivalent in the end. Okay, so I'm already running out of time, so let me mention two things. So this pair that you construct is U and this VL. They don't need to be completely orthogonal, right? So the one thing that's missing is we would also want the left orthogonal like depending on the pair util, v tilde that also satisfies to make maximum argument to make that work. So this one doesn't satisfy. However, if you apply the same the dual construction using right acyclicity to this pair UVL, you get precisely the pair that has both orthogonality conditions. However, that doesn't need to be a T-structure in general. And yeah, we are not quite like that. And the second thing, I think I mentioned an abstract, but now I guess, so I should say at least a word about it now. There's another construction using using modules over E. So we have another construction. So there's another construction. So there's an equivalence if you look at all functors or all modules over E that have a revolution with an X revolution. What I mean by that is F is the co-kernel of the unida of a differential of a complex that's left E cyclic in negative degrees, modulo the faceables, and then you should equip this an exact structure coming from this big abelian thing. Then that's actually an equivalent. So those two categories are the same. So in some sense, pick whichever setting you like more. I'm kind of more derived category and T-structure person. So that's why that's the moment I presented. Thank you.
Any questions? I have a very nice question. I think why would you be interested in the T structure? Having the T structure first question. And second question, maybe you have already answered it. How would you find this object in nature, for instance, with presentation theory in this realization? Why would you be interested in that?
So I mean, okay, so maybe you want to look at T-structure, maybe you want to kind of have a small category that's already describing a whole derived category, so you have less information to use. So it depends a little bit on from which angle you come. But I mean, T-structures actually say a lot about, I mean, I know people classify all T-structures, for example, they can say a lot about the category itself. So they do contain some information. Alternatively, you might want to, yeah, what's the most information I need? What's the least information I need? And the other thing, the T-structure will always give us an abelian hull potentially, which in general here is not true, but abelian categories are always nicer, of course. So yeah, there are various reasons, yeah.
Any other questions or remarks? If not, let's then the speaker again. And the next talk will start in 7 minutes.